Hi, welcome to Veteach. Now we'll be discussing about the reflector antennas. First, concentrate only on the concept. So here in reflector antennas, why they are being used? The term itself says I am using a reflector which is going to act as an antenna to me. It means that I am going to place a reflector to attain my desired radiation pattern. Remember, I am going to use reflector to attain my desired radiation pattern. So that is the reason it is considered to be as reflector antennas. In this reflector antennas, we will be saying that these are effectively used only to modify the radiation pattern, not to create the radiation pattern. These are used only to modify the radiation pattern which is been defined from a radiating element. And example, if a backward radiation needs to be eliminated, then I need to place a reflector with a large enough dimensions. So based on that, I'll be able to minimize the minor lobes which are being created. So I need to have these characteristics, that is large, suitably shaped, illuminated reflector. Everything should be there to predefine the characteristics of a particular beam. Based on these characteristics, I'll be placing the required reflector in such a way to modify the current radiation pattern and to minimize the minor lobes as well as side lobes and the back lobes. So coming to this concept, the first concept that we need to discuss about is flat sheet reflector. Here the flat sheet reflector term itself says that I am using a perfect conducting plane which is being placed along the length at a distance s. It is considered to be as flat sheet, and I'll be handled this mechanism by the image method. That is, I will be able to define the concept of reflection or the reflector property in a flat sheet conductor. So in the diagram, if you see that I am placing a particular antenna at a distance s at a flat sheet from a flat sheet, and at the same distance from the flat sheet on the other side, I'll be assuming the image of it. Now from the image to the antenna, the total distance will be 2s to me. So antenna to the image distance will be 2s. It means that exact reflection of the antenna is being taken on the other side, which is always an indication of a horizontal antenna. Assuming that I am not having any losses in it, then the gain of the field intensity of this is being given by GF. So here GF stands for gain of the flat sheet, and it is always given by 2 into square root of R11 plus RL by R11 plus RL minus R12. Here what is this R11 R12 is that when we are being considering it as resistances in two port, then I need to consider this R11 and R12. So that is the reason here the gain is being expressed in that way, 2 into square root of R11 plus RL by R11 plus RL minus R12 into modulus of sin R cos phi, where sin SR is equal to 2 pi s by lambda. As I said earlier, the spacing is always important. With wide spacings, I will be having the gain as less. But even though the gain is less, the bandwidth will be larger. So an antenna loss resistance of 1 ohm, the spacing is of 0.125 lambda, yields the maximum gain. So this is an assumptional case where we are being defining this horizontal antenna. As this flat sheet antennas or reflectors will be able to convert the bidirectional antenna array into unidirectional systems. That is, this reflection sheet will be reduced in size, and it is going to define in three principal regions. So that three principal regions will be explaining us. So in what way the analysis is much simpler in this flat sheet reflectors. The first region 1 is considered to be as above or in front of the sheet, in which I'll be having the radiated field by both incident wave as well as reflected wave. So in region 1, what is that? I'll be having incident wave as well as reflected wave. So the resultant field will be decided by both the fields. Whereas in region 2, I'll be saying that which is above and below the sides of the sheet. In this region, I'll be having only direct field. That is, it means only incident field will be taken, or else we can say that it is just a shadow to the reflected field. And region 3 is said to be below or behind the sheet. In this, we will be having a complete shadow region. That is, we will not be able to see the incident field pattern as well as reflected field pattern. Only diffracted fields will exist in this region 3. So narrowing these reflecting sheets will always result in more radiation to us. So more than, we can say that, what is that is, to have an effective radiation, we can consider region 3 is the best. But in region 3, we will be having diffracted region or the radiation that is going to be present, and it can be minimized by using rolled edge or else absorbing materials. So if we use both these elements, then obviously we will be saying that we can have effective radiation that could be present in the region 3. So this is of the flat sheet reflectors. So this concept can be extended with the help of another flat sheet. So if this has been extended with the help of another flat sheet, we will be calling it as corner reflector antennas. In this, two flat reflector antennas are been meeting a point with an angle. So that angle we will be calling it as a corner form, and this corner form structure will be giving us an effective directional pattern to the existing beam, and it is always considered to be as driven antenna. Remember, we said that reflectors in reflector concept as well as in director concept, the parasitic elements will be considered. So the parasitic elements, what is that is, they will be acting as reflectors as well as driven elements or directors. So here, what is that is, when I use flat sheet parasitic element, then I will be calling it as reflector element itself. But in parasitic element, it is dependent upon a driven element. But here, when I am using two flat sheets, that is two reflectors, if I am using, then obviously this parasitic element is going to be converted as a driven antenna or else driven element. So which is always a half wavelength or a half wave dipole, and meeting at a corner, as I said earlier. And this is the representation here. If you observe, I have taken in two different images here. One is showing on the right hand side, the other one is showing on the top side. So if you observe that this one square structure is representing one flat sheet antenna, this is another flat sheet antenna which has been connected to it with a variation of 90 degrees. So here one flat sheet is being taken with 90 degrees variation. I has taken another flat sheet. So both the flat sheets right now are being connected. So in between these, what is that is, I had used a dipole antenna that is been placed through the coaxial cable or the transmission line, or a dipole is been fed by coaxial cable. So on placing this, what happens is that I'll be having an intersecting axis. So main or intersecting axis will be there where the radiation pattern will be more directive. Here I am showing the same diagram in a top view. That is, here I'll be placing two flat sheets. In between I am placing a dipole. So one is vertical, the other one is horizontal. So now when placing this, if I am going to have beta equal to 90 degrees, that is the meeting angle between the two flat sheets is 19 degrees. So it forms a square corner reflector and it is always effective in wide range of angle of incidences, that is 0 to pi by 4. So wide range of angle of incidences means we'll be having a maximum directivity that could be attained. And the reflected wave is always directed along the path of the incident wave. So when square corner reflector is formed, what does that? The reflected wave will be included to the incident wave. Now what happens when reflected wave includes with incident wave? More directivity will be attained. The next case, if I am taking the two flat sheets are been meeting with an angle 180 degrees. 180 degrees means cascading the back to back, which is said to be as equivalence of the flat sheet. So this is the limiting case where we cannot consider it, but it may be analyzed by method of images. So which is given by beta equal to 180 by n. And the field patterns that we need to study here is on the basis of equivalent circuits or making it as a two-port network. So the field patterns here are being given as E phi theta equal to k bar square root of p by r11 plus r12 minus 2 r14 into cos beta d cos theta minus cos beta d sin theta, where p is the power supplied and k bar is the constant involving the distance r, and the gain is being given by square root of r11 by r11 plus r12 minus 2 r14 into cos beta d cos theta minus cos beta d sin theta, where this entire term, cos term, is being considered to be as pattern factor, and this particular square root of r11 by r11 plus r12 minus 2 r14 is being taken out as coupling factor. So this pattern factor and coupling factor will give us the more relationship in what way the beam pattern is more directive. And if I am going to take maximum radiation here, the theta is always considered to be as 0. So when theta is being 0, then the gain consideration will be taken out as square root of r11 by r11 plus r12 minus 2 r14 into cos beta d minus 1. So assuming that these conducting sheets or reflecting sheets are perfectly conducting and are of infinite size, then these formulas are going to exist, and the power gain is always 10 to 20 times obtainable with this corner reflector antennas when compared with normal antennas. And if they are being used effectively in point-to-point communications as well as in radio astronomy applications, these corner reflector antennas are being used to have effective directivity. Thank you.